Hello everyone, my name is Pauline Op de Beeck, Environmental Portfolio Lead for AII, and today we'll be doing a demonstration on how to use the Ready Reckoner Solutions Impact Evaluator, a key tool in order to complete the CSP grant application. And I'm joined by Phil, a member of our advisory council who has developed the tool and will be explaining the logic and data behind it, as well as giving some examples that you can also find in the guidance on how to calculate your impact in the tool. Over to you, Phil.
Thanks very much, Pauline. My name is Phil Patterson. I'm a member of the CSP Advisory Council. I'm a dyer. I've been working in the industry 35 years, and I've been working with AII to develop tools to enable grant applicants to assess their solutions, and so that we can objectively compare different solutions across a wide range of different topics in the world of textile production. The first thing I'd like to do is just give a little bit of background on the information that we have got that helps us make these objective evaluations. So we've created a data file, and in there we have got all processes from fibre through yarn manufacture, fabric manufacture, wet processing, and garment manufacture. And we've split these down into individual processes and even into sub-processes. So for each fibre type and each process type, we have got the amount of material that is actually processed. We have got information on the kilowatt hours per kg, the energy use in the process, and this is from actual factory data, also from some software modeling, and from taking advice from experts in various parts of the textile supply chain. So we get a figure of kilowatt hours per kg. We have a conversion factor of the amount of CO2 that is emitted per kilowatt hour. And the way we do this is we have got an estimation of the on-site fuel mix for steam, heat, electricity, with an emissions factor for that, using just internationally sort of agreed emissions factor. We have an average for grid electricity, a global average, and we have a nominal split between 80% on-site energy and 20% grid for the electrical energy. And this creates a conversion factor of 279.82 grams per kilowatt hour. So what we have in the data file, we have got the kilowatt hours per kg. So in this case, for polyester fabric dyeing, we've got a model process using a scour at 60, a dyeing at 130, and a reduction clear and a wash. We've got the individual sub-processes also split out to look at the energy use per sub-process, and we calculate the grams of CO2 default per kilogram processed. We've also got a split in there for heat and electricity, which for most wet processors is around 65% heat, 35% electricity. And then we can calculate the grams of CO2 that are generated because of heat energy and electrical energy. And ultimately what this calculates through is the total amount of CO2 emitted for that process. We can split it by heat and electricity, but it gives us a percentage of what we call the gas cloud. So we've got a total gas cloud of CO2 emissions that the textile supply chain is responsible for. And you can see here with polyester, it's a very popular fibre. It's a warm scour, it's a warm wash off and a hot dyeing process, and it actually accounts for nearly 17% of all emissions. So this is something that is a significant process. We've got all these figures for different fibre types, different processes, all the way through from fibre manufacture, yarn manufacture, fabric manufacture, wet processing, and garment manufacture. And that's just to give you a background of the data we've got. Now, a lot of this data we think is quite solid data, but we do welcome feedback over time to improve it. We're always open to constructive criticism. And if anybody thinks we've got any data wrong when they put through an application, then we'll, of course, have a conversation with people. We're not saying this is right. This is a model. This is something that we're quite confident in, but we're not saying for a moment this is 100% correct. But it's just to show you the process that we're using. I'd now like to just take you through to the Ready Reckoner itself and explain how that works. So the Ready Reckoner reads from the master data file. And what we've created here is something that is very, very simple to use. We'll be using it to check applications, and we want applicants to use it to provide us with information with their applications. And this is very, very simple. It looks complicated. There's a lot of lines and information on there, but this is all locked apart from a few key cells. So the first thing I'd like to do is take you through an example, which is similar to one of the first round of grant applications that was successful. And this is a wet processing facility improvement program that can be applied globally, that can save 10% of heat energy, 5% of electrical energy. So we'll go through the way we would do this and how you should do it. So the first thing to do is to select from the wet processing box. This is for information only. This isn't involved in any calculations, the box here on tiers. What we then do is we go down to wet processing. And because this is a wet processing facility-wide project, we select all wet processing. What that then does is that automatically calculates the percentage of the gas cloud that is in scope, the reach of the application, and that is 41.6% of CO2 emissions. Now, this was provided to us by WRI, and we made some adjustments to that, but this is our figure for the total amount of CO2 emissions for wet processing. Wet processing is a very energy intensive process. We then enter the figures for electricity savings, 5%, as we said before, and 10% for heat. And this then calculates the maximum potential savings in terms of megatons of CO2 and tons of CO2. And you can see there that represents potentially 3.4% of the gas cloud, which is a very, very significant amount of CO2 savings. We then go on to the geographical limitations. Now, in this case, it is globally applicable, so we would leave it as you receive the Ready Reckoner, with the solution applicable globally ticked as yes. If you find it is on no, which you shouldn't do, but just put it back to yes. And then this just carries through the 3.43 to say there are no geographical issues with the project. We then look at the scale up and rollout. And this is something where you've got to provide us with a reasonable projection of how quickly this can scale up and what amount of the maximum potential savings you can achieve. So if you are going to roll something out to 2 factories, the percentage of the industry that's affected is going to be tiny. If you can roll it out to thousands of factories, then that's going to be more significant. So in this case, just for an example, I'm going to say this is going to reach 1.5% of the maximum potential savings by the end of the funded project. And I'm going to say that by 2030, when the scale carries on going, it's going to reach 2.5. And then what this then does is calculates the projected annual savings by the end of the funded project. And it also projects the annual savings by 2030. Now, what this then shows us is that we're saving potentially 0.4 megatons per year by the end of the funded project, and 0.57, sorry, my eyesight is poor, 0.67 by the end of, by 2030. Now, if this was nominally a $150,000 project, we can calculate the cost per ton. So that is the way that the calculator works. I'll now show a different example, which is geographically restricted. So in this case, we're going to look at a solar PV project, which works in a country that represents 10% of all cotton weaving. So the way that we would do this is we would reset this, and we would go through again and say, in terms of fabrics, this is a fabric project because it is weaving for information only. And then in terms of fabric production, we would go through cotton weaving. You will notice here that we do have sub-processors for weaving, but because this is solar power, which is providing electricity to the whole facility, then we select the main headline figure for cotton weaving. In terms of effectiveness, then, as we mentioned in the introduction, it's going to save 25% of electricity, and it has no effect on heat. So we can see that this project is affecting potentially the reach is 2.73%, which is much less than what we showed with the wet processing project, but it's still significant. 2.3% of the total emissions is still a huge amount. And then the maximum potential savings after we put in the savings for electricity are 0.57%, which is 4.4 megatons. Then when we get on to geographical restrictions, what we have to do here is we need to then say it is not globally applicable, it is geographically restricted, and the percentage of relevant global industry that represents, and as we said in the introduction, that is 10% of all cotton weaving. Now, what we have also got with geographically restricted projects is, do we want to use our default emissions factors, or do we want to use local emission factors? So if you are doing a project that is saving electricity in a country where 90% of the grid is renewables, then we need to factor that in. If it's somewhere where it's a very, very dirty grid and there are no renewables involved, then we probably need to adjust things. Now, in this example, I'm not going to change anything because that can get quite complicated. And we'd expect applicants to have that information to hand when they put forward a geographically restricted proposal. The other thing to mention is that if somebody puts forward an initially geographically restricted proposal, but with an intention to be global eventually, you should use the default emissions factors, because it would only be relevant for the first phase of the project. Later on, if you then put it into other countries, the globally applicable emissions factors are far more relevant. So you can see here that we've got maximum potential savings of 0.57% of the gas cloud and 4.4 megatons of CO2. When we add in the geographical restriction, that drops down to 0.06 of the gas cloud and 0.44 megatons of CO2. When we look at the scale, obviously, if you're looking at a limited a geographically limited project, it's quite easy to imagine that you could reach quite a lot of those maximum potential savings because there's only a few facilities in that country. So in this situation, if you could reach 50% of those facilities by the end of the funded project, and you could reach 70% by 2030, we can then see this computes through to 0.22 megatons per year savings per annum by the end of the funded project, and 0.31 megaton savings per annum by 2030. So there's an example of how to do something with a geographical restriction. The next example I'd like to give you is to look at sub-processors and how you should manage sub-processors in the ready reckoner. So if we've got a notional new dye that enables polyester to be washed off in a single bath after it has been washed. If you remember, when we looked at the model processes, we had got a reduction clear and a wash after a typical polyester process. If we've got a notional new dye that halves the wash off energy and electricity by going down to a single bath, then that is something that we can put through the ready reckoner. So again, we need to make sure we've got the right boxes ticked. For information only here, we are putting in wet processing. And then in terms of wet processing, we look here at the polyester fabric batch dye, and we are looking at the wash off. So we select the wash off only. We select the sub-process. We don't have to select the main headline one. It's the wash off only. Now, of course, polyester can be dyed in fabric form. It can be dyed in yarn form. So we need to select the yarn and fiber dye as well. In terms of a continuous polyester dyeing, then that is a different wash-off process. So at this stage, I'm not going to include it. But if you were the inventor of that process and you could give us evidence that it did apply to continuous processing, then you would also add in the continuous processing of polyester. So this, with polyester still being a major fibre and the wet processing being a significant impact overall, this is still accounting for 2.07% of all emissions. That's the reach, the total reach. Now, if we then put in the electricity savings of 50% and we put in the heat savings of 50%, this then calculates through to a percentage of the gas cloud for maximum potential savings of 1.04%, which is 8.05 megatons. Now, of course, this one is geographically applicable because if it's a dye, it's not going to be only available in country A, B, or C. It will be globally applicable. So we need to reset this. You won't have to do this, hopefully, because yours will already preset on the no geographical restrictions. So we can just cross-check here that 1.04% of the gas cloud and 1.04 of the gas cloud here, there's no geographical restriction. Now, in terms of the scale up of introducing a new dye, then it's a massive industry, it's global, there's lots of dye houses, so it's likely to be quite low by the end of the funded project. So I'm going to put in here 2% of the maximum potential savings affected by the time we get to the end of the funded project. But if something is successful and is delivering huge savings, then the roll-up can sometimes be exponential. So I'm going to put in 10% here. And then this calculates through to 0.16 megatons per year. And also that's by the end of the funded project, and 0.61 megatons per year by the end of 2030, with the calculations there for the cost per tonne. So that is three very simple examples. I'd now like to look at a couple more slightly more complicated examples. And this is where we can use the Ready Reckoner as a tool, but it doesn't necessarily give us absolute clarity. So if we look at a recycling project that takes end-of-life dyed polyester garments, shreds them, and then uses the dyed yarns to make new yarns that require no dyeing, that can then be weft knitted into fabrics with no wet processing. Now, if we say this project aims to process 2,000 tonnes per annum by the end of the project funding and 10,000 tonnes by the end of, by 2030, then that is something where it would be a very interesting project for us. We know we've got to look at recycling and circularity, but in terms of calculating it, of course, we've got this based on a linear model where we're looking at fibres, yarns, fabrics, wet processing, garment making. Now, the key thing with recycling and circularity is to look at where the benefits are delivered. And we also should give innovators and solutions providers credit for the solutions that they provide. So if a material recycling project can theoretically mean that we've got less virgin materials made, we should credit the people who innovate the circularity solutions. So we would assume that virgin materials were not made in order to calculate the potential benefits. Whether that happens, it's out of our hands. It's quite often out of the solution provider's hands, unless they are actually the fibre manufacturer, which would be an interesting project. So what we need to do is to look at where the benefits are delivered and go through it in a logical way. So if you have got a situation with recycling of recycling of garments, dyed garments, we would need to, it wouldn't necessarily be applicable here. It would be outside that, and we'd ask you to provide details in there just to say this is circularity. But where are the benefits delivered? Now, the benefits are delivered at the fibre stage because we are not making virgin polyester because we're reusing the dyed fibres. And we would also look at the dyeing and finishing. We've still got to make yarns. We've still got to knit fabrics. We've still got to make garments. But we would be getting benefits in wet processing. So we wouldn't be dyeing fibres. So we would select the polyester dyeing options, the full processes, because we're not going to do any wet processing at all. And then what we would do is in the next box, because we're completely eliminating the need for these, we are putting 100% savings in there. So we would put 100% savings, 1000% is rather a lot, 100% savings in there. And this shows us that the potential here is enormous, because the reach is 25% of the gas cloud. That's what the polyester manufacture and polyester wet processing accounts for between them. And it's the maximum potential savings, because we're just not doing it, are huge. But then when we get into the detail of scale, this is where it starts to become more realistic. Now, at this stage, I'm going to say that this is globally applicable. It's not in one particular place. But what we've got to look at in terms of the scale is if we've got 2,000 tons from a figure that we have in our data of 45 million tons is 0.0044%. Which registers as 0 in here, just because we've got the box set at 2 decimal place. So what you have to check is in the box here that you're registering an actual figure. Now, if we have got, we said 10,000 tons, then we've got 0.0044 times by 5 is 0.022. So that then calculates through to figures of 0.01 megatons per year for at the end of the funded project, and the projected savings by 2030 are 4.35 megatons per year, which is pretty significant. So we can see here how we can use the Ready Reckoner to look at circularity and materials reuse by looking at where the benefits are delivered. I'd now like to take you through what is, again, we're using the tool. Sorry, I'd just like to go back there. Apologies for a moment. We've calculated the figure for the savings for the polyester reuse. But what we've also then got to factor in is what are the impacts of the actual recycling process. So we need to take the savings of the solution that we've calculated using a Ready Reckoner, but then we have to take off the impacts of the recycling itself to get a true figure. I'd now like to go on to the more complicated solution, and this really is using the Ready Reckoner as a tool. So we have a situation where we may have a quality improvement. And if we've got a quality improvement device that eliminates nylon weaving faults from 1% of fabric wastage to 0 fabric wastage, that sounds quite simple. But what we've got to look at is where are those benefits delivered. I'm not going to go through this calculation, but because it is quite complicated, but I'm going to explain the logic. Now, of course, we get the savings in weaving. We get the savings in weaving because we are not weaving faults. So we save 1% on the impacts of weaving. And we calculate that by selecting weaving from the drop-down box. We input 100% in the electricity and the heat, since we're eliminating those faults. Then we say that it's applicable globally. But then in terms of the scale, then we're looking at a small amount, 1% of the total amount of nylon that is used in weaving. We then have to be fair and say, if we're not weaving nylon, faults in woven nylon, we don't need to make as much virgin nylon. So we get 1% savings in virgin nylon manufacture. So you can go through the calculation to do that. You then have to look at the 1% savings in yarn, because we don't need to make those yarns either. So we get 1% saving in yarn manufacture. And then one thing that is a frustration for dyers like me, and a frustration for dyers around the world, you can't always see weaving faults until you've dyed them. So it may be that half of those weaving faults go on to be dyed and are then faulty fabric. So it's entirely reasonable to say, for example, 0.5% of savings from the impacts of dyeing woven nylon. So what you have to do here, you have to calculate 4 different calculations, sum up the total savings, and then of course you need to take off any impacts that the solution itself has. So if the solution is powered by electricity or powered by heat or steam or whatever it is, then the impacts of that solution need to be calculated and taken off the savings that we deliver. So that takes you through several examples of how to use the Ready Reckoner. It gives you examples of how you may use the Ready Reckoner to calculate things and where the information comes from. But one final thing just to mention is effectiveness. How to calculate the effectiveness of the solution to add in to these boxes here. Now, we mentioned on the data sheet that we have model processes. We ask everybody to look at those model processes and use them for comparative purposes. So if, for example, you have got a process which is looking at delivering savings for reactive dyeing of cotton on jet dyeing machines, we've got a 10 bath model process in there with 3 baths for preparation, a dye bath and 6 wash-up baths. We want you to use that to compare your solution. So if you are saying that you are saving 2 wash baths, but you've got a model process of a 3 wash off, then you're going to have much higher savings in your calculations. We want you to recalculate using those model processes. And what we have in the appendix here to the Ready Reckoner, we've got all those model processes here, and we've also got the kilowatt hours per kg of the process, and we've got estimates of the heat and electricity. So if you are looking at a solution that looks at the dye bath only for polyester, we would be asking you to look at the kilowatt hours per kg of 2.93 with a split of 65% heat energy and 35% electrical energy. And if you are only saving heat by dropping the temperature, for example, then we want you to do that calculation accordingly. And we've got model processes for all wet processes. We've got separated out for garment manufacture, sewing, laying, and laying, sewing, and finishing. We've got different processes separated out for fabrics in terms of the beaming, sizing, and weaving, and the beaming and knitting for weft knit. And we've got this for the whole supply chain in there. So when you're calculating your effectiveness, please use this as a guide. As I said before, we believe this is pretty good data to work with, but if you disagree with it, please feel free to contact us and say, we think you've underestimated this, overestimated that. We're working to improve this, and over the coming years, we will optimize this, we'll refine this, and we'll make it better and more relevant. But hopefully that explains things. But if everything isn't clear, please feel free to contact myself or to contact Pauline via AII, and we'll do our very best to help you. Thank you.
Thanks, Phil. And if you could just actually quickly go back to the Ready Reckoner, I just wanted to point out that when people do the application, they do have to put in their own grant project totals. If you go all the way to the right,
Yep.
where we've got the little arrow, it's currently set at $150,000. So obviously there you need to put in your project fee, and that will be different for everyone. And that's how we calculate the dollar per ton. And I've just noticed that the cells are in pounds. Please ignore that and assume that it's dollars. There's no currency conversion happening there. Just put in the figure that comes out into the application. Great. So yeah, that's all we wanted to go through today. Thank you so much, Phil, for taking us through. And as Phil mentioned, if you have any questions, please do contact CSPhelp@apparelimpact.com. Thank you all. Bye-bye.